our objective today is choosing whether it's a linear, a quadratic, or an exponential model. So we can use a linear, quadratic, or exponential functions to model sets of data. A linear equation, remember the line is a straight line, and you get y equals mx plus b. In a quadratic, you have a parabola, where your function rule is y equals ax squared plus bx plus c. Or you have an exponential function that rides close to the x-axis, it never goes underneath the x-axis and then quickly shoots up with a function rule of y equals a times b to the x power. So we can use a graph to help us choose whether it's a quadratic, a linear, or exponential model. So it says graph each set of points, which is the most appropriate for each set. So we have negative 3, 6, negative 2, 2, 0, negative 2, 3, 6, 1, negative 1, and 2, 2. And as you can see, I have graphed these. And if I were to connect to the dots, we would get a U-shaped graph. And now, this is a U-shaped graph. Well, the graph that is a U-shape is a quadratic. We know this is not linear because it's not a straight line. And we know it's not exponential because exponentials do not go past the x-axis. So being a U-shaped, then we would consider this to be a quadratic graph. Now B, we have negative 2, 5, 0, 3, 1, 2.5, and 2, 2. If you notice here, this goes in this direction. Well, this is not a straight line. It is not going to go back up. None of these are saying that it's going to curve back like a quadratic. This actually goes up and then it's slowly coming down to get closer to this x-axis. So this would represent an exponential function. And our last one, negative 2, 4, negative 1, 2, positive 1, negative 2, and 2, negative 4. As you can see, they line up perfectly. And if I were to connect the dots, I would make a straight line. An exact straight line represents a linear function. We can also analyze data numerically and determine whether it would be perfect for a quadratic, a linear, or an exponential. So if we look at this first table, we look at the x values, and all of these x values are increasing by 1 unit every time. Then we look over here, negative 2 to 2 is a positive 4, 2 to 6 is a positive 4, 6 to 10 is a positive 4, and 10 to 14 is a positive 4. So all the common difference between each of these is a positive 4, which means that it is increasing on our graph the same amount every time. So when you have a common difference of 4, when they are all the same, this represents a linear equation because that's how it makes that straight line. It's going up by the same amount every time. So you can find a linear is when the first differences are all the same. Now if you look at example 2, all of our x values still increase by 1. But if you notice our y values, they're all over the place. 16 and 2 is a difference of negative 14. 2 and negative 2 is a difference of negative 4. Negative 2 and 6 is a positive 6 difference. 4 and 20 is a positive 16. And 20 and 46 is a positive 26. None of these are the same number, which tells us it's not linear because they would all be the same number if it were to be linear. But if you do further investigation, you should notice that, okay, negative 14 and negative 4 has a positive 10 correlation, a difference. Negative 4 and positive 6 has a positive 10 relationship. 6 and 16 has a positive 10, and 16 and 26. So the second difference, so the differences in the first set of differences are all the same, which means that this is quadratic because the second common difference, so once you find the differences of your original the differences of those, if all of these second differences are the same, then it is quadratic. And our last example is a little bit different. When you're dealing with exponential, you're not going to be looking for the differences, you're going to be looking at ratios, which means we're going to be looking at what we can multiply. So here we have our differences are all 1. But then here, negative or 1/9 to 1/3, if 1/9 times 3 gives us 1/3. 1/3 times 1 gives us, or 1/3 times 3 gives us 1. 1 times 3 gives us 3. 3 times 3 gives us 9. So these are increasing by a factor of 3. When you have a common ratio, so the same number being multiplied by all of these, then it's going to be an exponential. The reason for this being a multiplication instead of the differences like the other two is because exponentials shoot up really quickly. The way to do that is raising something to a certain power. So here, our common ratio is multiplying by 3. Since it's a common ratio, then it's going to be exponential. Any exponential, the ratios are all the same, or the factor that they're dealing with. So now we're going to take the two components that we just talked about, graphing points and seeing what the shape of the graph is, and analyzing data points to figure out a modeled equation for the information we were given. So it says, which kind of function best models the data? Write an equation to model that data. So we're given this information. Step 1 is going to be to graph your information. So if you see here, I have graphed these points. And if you notice, it starts up way high and it goes down quickly and it's starting to hug the x-axis. It has not gone below the x-axis. So looking at the shape of this graph, it appears to me, making that kind of L shape, to be an exponential. But this graph only is what it appears. We need to make sure. So then our next step is to do what we did in the slide before and test for a common ratio. We know exponential functions have to have the same factor every time, the same common ratio. So from 20 to 8, so 8 divided by 20 is 0.4, because 20 times 0.4 gives me 8. 3.2 divided by 8 is also 0.4, so 8 times 0.4 gives me 3.2. 1.28 times divided by 3.2 is also 4.4, and 0.512 divided by 1.28 is also 0.4, which means all of these numbers are being multiplied by 0.4 to get to the next one. They have a common ratio of 0.4. So now we have the shape of an exponential, and we have all of these have the same common ratio. So those are two things that tell us that this is going to be an exponential function. Well, we know that the general in step 3 that is to write the actual model for this function. Well, we know an exponential equation is y equals a times bx, where a is your initial amount. So that's normally when x equals 0. And then your b is your growth decay factor. So that's your common ratio that you found in step 2. So we have y equals 8, because if you look here, when x is 0, our initial value was 8, times my common ratio of 0.4 we found in step 2 to the x power. So this is the equation that we think best models the information we were given. But we always need to make sure that we check to make sure that that equation is correct. So step 4 is to test points to check. So we're going to use some of the points in our table to make sure that they actually work in our equation. So I have y equals 8 times 0.4 to the x power, which is the modeled equation that we came up with. I am going to test when x is 1. So I plug in 1 for x, and 8 times 0.4 to the first power is 3.2. And 1 and 3.2 was one of the points in our table of data. Well, you always want to check more than one point because it could work for one and not for any of the rest. So I'm also going to check when x is 3. When I plug the 3 in for x, I get y is 0.512. If I look, when x is 3, y was 0.512. So both of those points work, which tells us that the equation for this data is y equals 8 times 0.4 to the x power, which means that it is an exponential function.